In this work, we consider the problem of assembling complex industrial objects that have parts of varied shapes, sizes, and needed intricate maneuvers for assembly. Given a stepwise manual with diagrams and text as shown on the left, we aim to assemble the corresponding set of 3D parts, which are represented as 3D point clouds in the physics engine-based virtual environment, outputting its stepwise assembly trajectories, which can be rendered into 3D animations as shown on the right. As existing datasets focus on simplified assembly scenarios, overlooking shape complexities and assembly trajectories in industrial assemblies, we introduce AssemblyBench, a synthetic dataset of 2,000 industrial objects with automatically generated multimodal instruction manuals, corresponding 3D part models, and the part assembly trajectories. Here we show the pipeline we present for automated instruction manual generation that we develop in order to create AssemblyBench. From CAD model of an assembled object, we find the part assembly trajectories using a physics engine and import the animations to Blender. These Blender renderings are then used to prompt a large vision and language model to create CAD part names and text-based assembly instructions. Here, we showcase a range of example assemblies from our AssemblyBench dataset. We provide diverse assemblies where parts vary widely in shape, size, and geometry, and each assembly follows its own unique motion trajectories. A key challenge is correctly matching the part names and the diagrams in the instruction manuals to their corresponding 3D point cloud components. But here we go a step further. Every assembly in AssemblyBench must also be physically realizable in the simulator. This means that the predict motions must obey real-world physical constraints, making the task substantially more demanding. Altogether, AssemblyBench presents a rich, realistic, and truly challenging benchmark, one that captures the complexity of genuine industrial assembly process. To tackle the challenges posed by AssemblyBench, we introduce AssemblyDyno, a new transformer-based architecture designed to predict both the correct assembly order and the full 60 degree of freedom motion trajectories of every part. AssemblyDyno learns to align the stepwise instructions with the corresponding 3D point cloud parts using a powerful soft attention mechanism. This allows the model to understand which component each instruction refers to, and how that component must move, both in translation and rotation, to complete its assembly. For every part, AssemblyDyno predicts a discrete sequence of physically meaningful transformations, effectively charting the entire motion path needed for successful assembly. And importantly, it does all of this jointly, producing the full set of assembly trajectories in a single forward pass. Here, we show an example assembly produced by AssemblyDyno on an AssemblyBench instance. We now compare example assembly trajectories and the final part locations determined by AssemblyDyno to the output of manual PA, the previous state-of-the-art method. As you can see, AssemblyDyno generates motion trajectories that are far more realistic, closely matching the true assembly process and capturing the subtle motions that previous approaches miss. Here are more examples of assemblies produced by AssemblyDyno. We showcase a broader set of qualitative results from our method. These examples demonstrate AssemblyDyno's ability to navigate complex geometries, interpret instructions, and generate smooth, realistic assembly motions across diverse cases. Here, we show some scenarios that illustrate why a physics engine-based evaluation is important. As is clear, some of the predictions by our AssemblyDyno model, while plausible when considering 3D point clouds, is clearly infeasible when physics simulation is involved. Thus, using this simulator provides a stricter evaluation of the prediction quality. On this slide, we compare state-of-the-art methods on the AssemblyBench dataset on a variety of settings, including comparisons on predicting the part order, final assembled poses of parts, and the assembly trajectories. Our evaluations also uses a physics engine, as shown on the right. In summary, our contributions are threefold. First, we built a dataset includes complex industrial part assemblies with multi-model user manuals and assembly trajectories. Then, we proposed a generalized feed-forward model that takes in multi-model assembly steps and 3D part point clouds, predicting the parts assembly order, final poses, and assembly motion trajectories. Finally, we designed a physics engine-based protocol to evaluate the physical feasibility of predicted assembly trajectories, where our model shows state-of-the-art results. Please visit our website for project details, dataset, and code repository. Thanks for watching.